Hey guys, Mr. T here. This is another video. This one is on additional constraints. So often it's necessary to deal with multiple constraints at the same time when dealing with two variables and the relationship between them. So we're going to continue by continuing the example, considering the example from 2A1 feasible regions video. You might remember the constraint was that the total spend has to be $20, or we eventually started saying that it was less than or equal to $20. So therefore 0.4x, 40 cents per sausage, plus y, $1 per sausage, had to be less than or equal to 20. But what if there were added requirements to ensure a successful barbecue from that example, or let's say there was a minimum order of sausages and steaks from their supplier? So we're going to add some more constraints to this particular problem. For example, using that same example, because this graph was already hard enough to draw, what if Jason and Kate were required to buy at least 10 sausages and at least 6 steaks? This results in two more constraints to what we had before. X, which is the number of sausages, has to be greater than, and because we're saying at least, it can be 10 or more, so greater than and or equal to 10. It's not just going to be greater than, because 10 is acceptable. That's the least that we can have. Now y, at least 6 steaks, so once again it's greater than or equal to, because 6 steaks is acceptable, that's the lowest we can go, so it's greater than or equal to 6. So that totals our constraints to 3 different constraints. We have, and I'll try to draw them in green. So overall our constraints now are the one carrying on from before, 0.4x plus y is less than or equal to 20. And now we have x is greater than or equal to 10, and y is greater than or equal to 6. Right now, we do not have those constraints drawn up on the graph, and the whole purpose of this is to show you how to draw them on. So hopefully I'm not going to struggle so much with drawing these straight lines onto this very slippery screen, but I'll do it anyway. X is greater than or equal to 10, so that is a line, and because it's defined by the x coordinate, it must be a vertical line. So it starts at x is equal to 10, and it's a vertical line from there. So the first constraint is this vertical line, like that. That's a x is equal to 10 line, okay? X is greater than or equal to 10 in this direction, and x is less than or equal to 10 in the left direction. So that's our first constraint drawn on. Y is greater than or equal to 6. So we draw a line at y is equal to 6, and that forms our constraint. So this may be harder because it's a longer line across for me to keep the ruler not sliding around. Fluke that one. So in this case, below this line is y is less than or equal to 6, and above the line is y is greater than or equal to 6. So now our feasible region is more complicated. Obviously, it doesn't start here, because these new constraints are telling us that the number of sausages has to be greater than or equal to 10. So to the right of the x is equal to 10 line, that constraint saying that we need greater than or equal to 10 sausages. And the other constraint is telling us that the feasible region has to be above the y is equal to 6 line, because we need to buy more than 6 or more steaks. But then at the same time, our original constraint was 0.4x plus y is less than or equal to 20. So this diagonal line is the 0.4x plus y line, then it has to be less than 20, so it has to be underneath that diagonal line. Therefore, overall, our feasible region is this smaller triangle within those constraint lines, okay, and following their greater than or equal to or less than or equal to signs, okay. So the feasible region now is a smaller triangle. It doesn't start at the origin. So now all of these results with inside are considered feasible solutions, but also the very points on the edges as well are feasible regions. This now has a special name. When the feasible region doesn't start at the origin, it's called a simplex. Does not start at the origin, which is 0, 0. Okay, so now it's called a simplex because it's like enclosed by multiple constraints, and it doesn't start at the origin. And these corners are called vertices. A single one is called a vertex. Vertices, plural. Okay, so if we're talking all of the corners, we're talking vertices. If you're talking about one, it's called a vertex. So any of these whole number points within the feasible region and on the lines forming the boundary and including the vertices are all possible solutions. Okay, so for example, if we looked at this bottom vertex here, which is 10, 6. Is that a possible solution? Well, 10 times by 0.4 is $4. Plus 6 is $10, so that's less than $20. That's fine. That's the cheapest that you could spend, actually. If we look at this solution here, 10, this vertex, sorry, 10, 16. 10 times by 0.4 is $4, plus 16 is 20, so that's spending exactly $20 and buying as many steaks as possible, but still meeting the requirement of 10 sausages. And this other vertex here, so you can think of the vertices, as the extremes as well, considering the new constraints. So here we have 35 sausages and 6 steaks. What is 35 times by 0.4? Can't do that in my head, need to use a calculator. 0.4 times by 35. 14. So that's a $14 spend on sausages with 35, plus 6 is 20. So this, considering the constraints, is the most sausages you could buy, 35 of them, while still purchasing the minimum number of steaks. So hopefully that shows you that the vertices, the corners of all of this simplex are feasible solutions as well. So the take home to get is that, I need my blue pen. Feasible region is now called a simplex. Doesn't start at origin. And what else is there to take home from this? All whole number points within simplex. Within simplex, on boundaries, so on the lines, and on corners, they're all feasible solutions. So we have another way of representing all the possible results, a bit more limited now because we have 2 added limitations here. Alright, so hopefully that helps you out with the idea of added constraints. It's getting a bit trickier now. it's time for you to do some exercises where you're looking at different situations and deciding on what the simplex will look like. Alright, I'll see you in the next video.